Hello everyone, I'm Xiao. I'm very glad to present our paper, Testing High-Performance Numeric Simulation Programs, Experience, Lessons Learned, and Open Issues. This paper focuses on the testing of a particular sort of programs, named high-performance numeric simulation programs. These programs are used to simulate complex real-world systems on high-performance computers, according to mathematical and physical models. They play a crucial role in modern science and engineering. For example, the formation mechanism of 100 disclosure loops, which was regarded as a 50-year-old radiation damage mystery, was revealed based on large-scale molecular dynamic simulation. Our work is based on a national R&D project whose goal is to create a virtual reactor, a system that is able to achieve the multiphysics and multi-scale simulation of a reactor core to support the design and analysis of a nuclear power plant. For instance, if we need to know how thick the wall of the core should be built, we can ask the virtual reactor to do some complex simulations. Assume that the simulation results tells that 10 meters are solid enough to protect the reactor, and based on this result, we build the reactor. But what if there's a bug? Obviously, high-performance numeric simulation programs must be systematically verified, and that is my job in this multidisciplinary project, led by domain experts. The goal of this paper is to present our experience of testing the simulation programs of virtual reactor. For better discussion, we set up 4 research questions. RQ1 is about the testing approaches. RQ2 is about the test inputs. RQ3 concerns test oracles, and RQ4 considers the bugs. The basic information of the programs under test is listed in the table. There are 5 programs, namely ANTMOC, MISA-MD, MISA-SCD, MISA-RT, and SINA. The 5 programs cover different application domains, such as neutral particle transport, molecular dynamics, and cluster dynamics. They vary in their size and programming languages. In general, they have many parameters and produce complex outputs. The common structure of the program under test can be depicted as this picture. They usually consist of a pre-processing module, a main calculation module, and a post-processing module. The programs have some characteristics. First, the computation pattern is generally a loop. Second, the entire computation, even deployed on a supercomputer, may require thousands of core hours. Third, the computation may be stochastic. Fourth, the computation is by nature inaccurate due to the multi-level errors, such as inaccurate input, imprecise physical and mathematical models, and floating point arithmetic. Finally, the programs have complex input and output. They have lots of parameters, and a single parameter may also be an external file that describes the geometric shape and the metal material. Moreover, the output may contain several gigabytes. We followed a very natural work procedure to test the 5 programs. First, when developers regarded that their program was ready for testing, they sent the program to us. Then, we collect possible test inputs and oracles and test the program collaboratively with developers and domain experts. If the program fails the test, then we ask the developers to fix the program and rerun the test. We tried several testing approaches, including classical testing, differential testing, property-based testing, metamorphic testing, Richardson's extrapolation. We will discuss them later. And this table summarizes the total numbers of test cases, properties, and metamorphic relations that were used to test the programs. You can see that we suffered from a shortage of test cases and severe oracle issues. And this table summarizes the numbers of bugs we found by adopting our approach. In total, we found more than 33 bugs. Please keep in mind that this project is mainly dominated by domain experts and HPC experts. We worked under the pressure of time, burden, and resources, and the project leader. We are not allowed to fully explore all the possibilities, as we usually did in the study of software testing. Now we'll begin to introduce the details of applying our testing approach. First, let's consider the classical testing. To apply classical testing, we need a test case that contains both the input and the expected output, and then check whether the actual output is equal to the expected. We applied classical testing to 4 programs. However, we only developed 12 test cases in total, which are obviously insufficient. Regarding checking the output, we also encountered some difficulties. For example, for Antmok, we can only check whether the actual output is close to the expected, since it's never equal to the expected output. For MISA SCD and MISA RT, we can only do wither comparison because the expected outputs were presented as figures in literature. For SINA, we can only ask the domain expert to check the result because the expected output is confidential. To apply differential testing, we check whether the actual output of the program under test is equal to that of a comparable program. The major difficulty is that not all the programs have fully comparable versions. For example, for Antmok, the open source program OpenMOC is only partially comparable because it does not support fast reactors. We found 9 bugs by using differential testing, and SINA contributed 7 of them. Because SINA is a rewrite of function program Frapcon, we are able to verify every function in SINA. To apply property-based testing, we need a property P and check whether P holds for every input and the corresponding output. The key is whether we can define effective program properties. The properties may be derived from physical models. However, it is too difficult for us to do so due to the lack of mathematical skills and the domain knowledge. The properties may also come from the program implementation. Such kind of properties are easy to define but may be ineffective to detect bugs related to numerical algorithms. In practice, we defined 17 properties in total. You can see that all the properties are very simple, but they helped us find 18 bugs. Metamorphic testing is an innovative testing approach that is developed from the property-based testing. The basic idea is to use a metamorphic relation R, which is a necessary property, to check whether a source test case and a follow-up test case can make R satisfied. Similar to property-based testing, the key to metamorphic testing is to define high-quality metamorphic relations. We encountered the same difficulties as we faced in property-based testing, but the situation is worse. We find that the metamorphic testing is much harder to be understood by domain experts and HPC developers. However, without their help, we cannot identify good metamorphic relations. In our practice, we identified 10 metamorphic relations. Here are some examples. You can see that these metamorphic relations are very domain-specific. The 10 metamorphic relations helped us find 8 bugs. Richardson's extrapolation was proposed by the scientific computing community and was used to verify many numerical algorithms. When the program has a step size h, the following equation must hold. The equation is a very strong mathematical property, and it is very sensitive to bugs. It can be viewed as a special metamorphic relation. However, this approach has low applicability. It requires that the program's math model follows a certain format. We find only MISA RT and SINA satisfy this requirement. Besides, the approach doesn't provide rich information for debugging. So although MISA RT failed the test, we don't know the reason until now. Finally, we also find that the equation may not hold if the implementation does not strictly follow the math model. However, the deviation is possible and common, for example, due to performance optimization. Now, let us consider our research questions to summarize our real experience. Our first question is what approaches are applicable and effective? We tried 5 testing approaches in our practice. Generally speaking, property-based testing and metamorphic testing are 2 most applicable and effective testing approaches. The main difficulty is that the 2 approaches are not very easy to be learned, especially by domain experts. Consequently, defining program properties and metamorphic relations becomes more challenging. However, even with simple properties and metamorphic relations, we still found many bugs. Hence, we recommend these 2 approaches. Regarding other barriers, the scalability, the portability, and support for multiple programming languages cannot be neglected. Many program analysis and testing approaches cannot be used due to the scalability reason. For instance, we try to use FPDebug, a dynamic floating point error analysis tool, to examine our programs. However, when FPDebug is turned on, the program becomes around 400 times slower. Since our programs may require thousands of call hours to return a result, FPDebug cannot be used in this situation. Portability is another issue. Our programs are usually run on a supercomputer, on which most existing software testing tools cannot be used. Our second question is where we can find test inputs. In our practice, we collected test inputs from domain benchmark problems, existing programs, literature, and experimental data. However, there are some pitfalls for our source of test inputs, so in general, we suffered from a shortage of test inputs. For example, if we want to reuse test inputs from LAMPS for MISA-MD, we have to do some non-trivial conversion due to the difference in input format and parameters. You may also wonder whether we can randomly generate new test inputs. Our answer is it's possible, but also difficult, because there may be some complex domain constraints over parameters. For instance, in MISA-SCD, CO is a value between 0 and 1. It refers to the copper content in an alloy. If it is increased to a certain threshold value, then the alloy may become not-salt, and many other parameters must also be adapted. The third question is what kinds of test oracles are there? First, we use numeric values as test oracles. However, because our programs are by nature inaccurate, the program outputs never match those values. A simple alternative, called oracle approximation, is to determine an error bound. However, how to define such a bound is another form of the oracle issue. We also used comparable programs as test oracles. However, when our program is different from the comparable program, there's always a dispute about which program is correct, because the comparable program may also be wrong. Visual results are frequently used as test oracles. It is a common practice in numeric simulation. Visual comparison is inevitable because in many papers, their results were only presented in pictures. However, visual comparison requires extra post-processing efforts and lacks automation. Domain experts often play a role of test oracles. We sometimes ask them to manually check whether the actual outputs were correct. However, their opinions are not always reliable. Different domain experts may also give inconsistent opinions. Necessary properties are also test oracles. As we have explained, it's very hard to derive necessary properties. Please look at this math model of MISA-SCD. It is completely out of our ability to interpret, analyze, and derive any property or metamorphic relation. The last question concerns bugs. In our practice, coding errors are the most frequent bugs. Athena contributed 11 of them. Athena is a rewrite of Frapcon, which was written in Old Fortran language. Many bugs can be attributed to the misunderstanding of the old code. After that, there are also many bugs in preprocessing parallelization and algorithm implementation. This implies that special attention must be paid to find those bugs. We found only one numeric error, but it is probably due to the lack of scalable tools that allow us to conduct systematic testing. Based on our experience, we propose the following test strategy. First, apply differential testing to compare put and its sequential version to find parallelization errors. The consistency between the sequential and the parallel version is also very helpful for debugging, since parallel programs are much harder to be debugged. Second, apply property-based testing and metamorphic testing to verify put because the two approaches are very applicable and effective. Third, if a comparable program P' is available, test put by comparing with P'. Finally, validate put with domain benchmark problems to address domain experts' concern. The last step is essential because domain experts usually value those domain problems highly. Another important lesson is that domain experts must be involved in testing. A very bad practice is to ask the necessary information from domain experts and then do it yourself. The problem is, much detailed domain knowledge about PUT may not be provided because domain experts do not know what information is necessary for testing, and neither you know. A good practice is to keep domain experts along with you forever. Since they are your boss, they may not want to help you. So probably the best practice is to become a domain expert yourself. We also notice that the use of PUT influences its testing. So make sure that you already know the intention of PUT before testing. Our last lesson is that we should preserve and manage the actual test outputs seriously. There are many benefits to preserve actual test outputs, although it may require a lot of storage. Based on our practice and observation, we also identified a few research suggestions. First, how to analyze and test a program in a context of multi-level errors is an interesting topic. As we have explained, there are many errors that may lead to an inaccurate result. When the program output is inaccurate, how can we know whether it is due to a bug in the program or an error in the input data? There is also urgent need for adapting existing or developing new testing techniques and tools for high-performance environment. However, doing so is non-trivial and challenging. We have to consider many practical factors, such as multiprocess and multi-thread execution, some special restrictions on supercomputers, and compiler friendliness. Third, in some domains, such as neutral particle transport, domain experts heavily rely on benchmark problems. However, from the perspective of software testing, those problems are very limited, and it's unclear that whether they are effective to detect bugs. Further studies on the development and assessment of domain benchmark problems must be carried out. Here comes the end of my presentation. Thank you for your listening.